2. Learning outcomes. Investigate what it means to do mathematics. Describe essential components of mathematical proficiency, including the importance of relational understanding, and connect learning theories to effective teaching practices. What does it mean to do mathematics? Doing mathematics means demonstrating mathematical processes, establishing the goals for students that reflect these practices, posing worthwhile tasks that open opportunities for mathematical processes to develop. Also, doing mathematics means generating strategies for solving a problem, applying that strategy, and checking to see whether an answer makes sense with the students. Also, we need to establish goals for students that reflect these processes and then posing worthwhile tasks that open up the opportunity for such processes to develop. A way to determine if your goals for students focus on mathematics is to consider the verbs in the lessons. Lower level thinking tasks do not adequately prepare students. Just listen, copy this, memorize this, drill this, compute this. Instead, we need to have higher order thinking that engages students, compare, contrast, explore, predict, investigate, formulate, verify, represent, model, justify your answer, generalize your answer, connect, construct it, critique it. Can your neighbor critique your answer? Can you critique their answer? These words look familiar to you because of higher order levels of Bloom's revised taxonomy. Where teachers focus on doing math, students are found, 1, to connect to previous materials, 2, respond with information beyond the required response, and make conjunctures and predict. Search for patterns. Begin with a number, start, and add, jump a fixed amount. For example, start with 3 and jump by 5s. You can ask students, do you see at least one alternating pattern? Have you noticed an odd or even pattern? Why is this pattern true? What do you notice about the numbers in the tens place? Do the patterns change when the numbers are greater than 100? You can ask them, have you thought about what happens to the patterns after the numbers are more than 100? For example, 113. One way is 100, 110, and 3 ones. Or you could say 11, 3, where the tens digit has gone from 9, 10 to 11. What happens after 999? See what they say. You can have these students change the start number to keep the jump number equal to 5. What is the same and what is different? Keep the same start number and explore with different jump numbers. What patterns do different jump numbers make? For example, the jump number was 5, the one-digit pattern repeated every 2 times, but what if it's 3? The length of one-digit pattern is 10. Do other jump numbers create different pattern lengths? Some teachers might be hesitant to let students use calculators, but calculators can help facilitate this searching for patterns. Using a calculator makes the list generate accessible for children who are younger, who can't yet skip. For example, 3 plus 5 equal, and then pressing equal time after time after time, it skips by 5, 5 more, 5 more, 5 more, etc. Another one, analyzing a situation. Ron's recycle shop started when Ron bought a used paper shredder machine. Business was good, so Ron bought a new shredding machine. The old machine could shred a truckload of paper in 4 hours. The new one could shred the same truckload in 2 hours. How long will it take to shred a truckload of paper if Ron runs both shredders at the same time? This is where we can let students explore on their own. Let's let students solve logically. Have you tried to predict approximately how much time you think it should take to the 2 machines? For example, will it be closer to 1 hour or 4 hours? What type of illustration might help solve this problem? Could you draw a rectangle or a line segment to strand for the truckload of paper? Is there a manipulative, like chips or pennies, you might be able to collect to make a collection that represents the truckload? The rectangle stands for a whole truckload on a sheet of paper. 1 hour, the machine will do half of this truck. The rectangle is divided in half. In 1 hour, the old machine can shred 1/4 of the paper because it used to take 4 hours. So 1 hour in one machine, 1 hour in the other machine. So half the truck is done by one machine, and 1/4 of the truck is done by another machine. So we have 1/4, 1/4, 1/4. So 3/4 is done. 1/4 of the truck is left. What is left is 1/3 as much as what they already did. So it takes the two machines 1/3 as long to do that part as it would take to do the first part. 1/3 of an hour is 20 minutes. So it takes maybe an hour and 20 minutes to do for a whole truck. When you add 7 plus 7, you get 14. When you make the first number one more and the second one number one less, you get 8 and 6. Is it still 14? That is true. You can also do this with different numbers. You can also do this with multiplication. 7 times 7 is 49. But when you go up with the first number, down with the second number, 8 times 6 is 48. So 7 times 7 was 49. 8 times 6 is 48. There's one in between. Have students try it a different way with, say, 5 times 5. It's 25. Go up 1 is 6. Down 1 is 4. 6 times 4 is 24. The difference between 25 and 24 is 1 again. Make sure you ask students, for what other problems is this pattern true? What else do you notice about the pattern? Why is the pattern true? You can compare the before and after products, draw a rectangle with a length and a height of each of the factors, and then draw the new rectangles. So you have 8 by 6 and 7 by 7. When you prefer, make sure to ask students, for what other problems is the pattern true? What else do you notice about the pattern? For the multiplication one, you can say, compare the before and after products. You can say, draw rectangles to represent each number with the length and height of each factor, and then draw the new rectangle, which would be 8 by 6. You can use stacks of chips. 7 by 7 is 7 stacks with 7 chips in each stack. And then the expression of 8 by 6 is 8 stacks of 6. Experimenting, explaining, explore. A good strategy for learning is to explore and concentrate and then analyze it abstractly. Helpful in situations involving chance and probability, or say with spinners. Who is most likely to win and why? For a person's turn, spinner A, then spinner B. Would it matter if spinner B first and then spinner A? How might you change one spinner so that Susie has the best chance at purple? One way to solve, you can make a tree diagram for A, for the 4 branches, and all the branches would have the same chance. So A would have red would have red, yellow, green, blue. Blue would have red, green, yellow, blue, and so would green and yellow. How is the relationship between the blue region and each other's? How could you make the tree for B with each branch having the same chance? You could use grids, partition squares to represent all the possible outcomes for spinner A and spinner B. If you use lines going all the same directions, and then the second one you can have lines in a different direction. And then you can overlap. Which colors actually make purple? And then decide what squares, how many squares, would actually represent purple. Answers. Notice that no answers were provided in any of the 4 questions. How do you feel about that? What about the right answers? What makes the solution to any investigation correct? That takes the explanation or justification and the reasoning that the student gives you to find if it's the right answer or the wrong answer. What does it mean to know mathematics? Understanding and knowing is a measure of quality and quantity of the connection between new ideas and existing. Knowing is not equal to understanding. Students may know something about fractions, for example, but not understand them. Procedural knowledge refers to how to complete an algorithm or procedure. Conceptual knowledge refers to the connected knowledge, mental connections among mathematic facts, procedures, and ideas. For example, a number of items of this list refers to procedural knowledge, beginning to find an equivalent fraction, and others refer to conceptual knowledge. Recognize 6/8 is greater than 1/2 by analyzing the relationship between the numerator and the denominator. Understanding exists along a continuum from an instrumental understanding, doing something without understanding, to relational understanding, knowing what to do and why. Manipulatives are physical objects that students and teachers can use to illustrate and discover mathematical concepts, whether made specifically for mathematics. A tool does not illustrate a concept. A tool is used to visualize a mathematical concept, and only your mind can impose the mathematical relationship to an object. Students to build connections among ideas, different representations must be included in instruction, and opportunities must be provided for students to make connections among representations. Students who have difficulty translating a concept from one representation to another also have difficulty solving problems and understanding. Students strengthen their abilities to move between and among their representations improve, such as from graph to words to symbols back to table, then to content, then to tools, then to diagram. Conceptual and procedural understanding. There's 5 strands: conceptual understanding, procedural fluency, strategic competence, productive disposition, and adaptive reasoning. If you don't have these 5 strands interwoven together, just like the diagram, that's where students are able to lose the connection, maybe not understand the problem. Conceptual understanding. The ratio 3:4 is represented with a manipulative and word problem, in words, graphing, table, and a diagram, and other types of ratios. Procedural fluency is they can count them all. They can do a traditional algorithm. They may have errors that we can fix by seeing it. Efficient standard generated strategies. They do it themselves. They come up with their own way. And they can count it out with their fingers. Constructivism theory. The heart of constructivism theory is the notion that learners are not blank slates, but rather creators and constructors of their own learning. They make networks and cognitive schemes that are the products of their constructing knowledge. They reflect thought is how people modify schemas to incorporate new ideas. They assimilation, new ideas fit with prior knowledge, the blue dots, and to the red dots. Accommodation, the new idea does not fit with existing knowledge. Socioculture theory, the mental process exists between and among people in social interactions. Learners, the zone of proximal development. An important aspect of this theory is that the way in which information is internalized or learned depends on whether it was within the learner's zone of proximal development, which refers to the range of knowledge that may be out of reach for a person to learn on his or own abilities, but they can learn with help. We don't need to pick between the theories. These theories are not teaching strategies, but should instead guide teaching. Implications for teaching mathematics: build new knowledge from prior knowledge, provide opportunities to communicate, create opportunities for reflection and thought, encourage multiple approaches to learning, engage students in productive struggle, treat errors as opportunities for learning, scaffold new content, and honor diversity. A proficient student may say yes to when you read a problem you don't know how to solve, you think, cool. Do you consider several possible approaches? Did you recognize the wrong pathway and try something different? Do you look for patterns across examples and try something new or find a new shortcut? As you work, do you decide to draw a picture, use a calculator, maybe model the problem with manipulatives? They would say yes to all of them.